All right, let's talk about LeetCode 1028, recover a tree from a preorder traversal. This one's kind of difficult, but when you break it down into chunks, it's not that bad. So if a node only has one child, the child is guaranteed to be a left child. This is really important. There's a left child priority, which really simplifies the logic and makes this problem easier if you understand how it works. But we'll come back to that. Basically, we're given this string. Dashes represent how deep in the tree relative to the root node we need to go to place the next node, and the values themselves represent the value we're supposed to give the next node. And one thing I didn't notice at first that really tripped me up that is important is that values can be multiple digits long. So we can't take like a single iterative approach where we look at index by index. We need to take kind of like a window approach when we're parsing this string and look at chunks. And what I mean by that is like if we're given an input, like let's say we're given this one dash 401 dash 349. We need to take windows of the string as we go through it. So like one would be a window, this would be a window, this would be a window. We want to get all the prepended dashes, and then we want to get all the number values before we see another dash. And that creates this window. Once we have that, we know we have everything we need to do the next action, which would be adding a node. So like this one would technically have 0 dashes prepending it. So depth would be 0, and then val's 1. But because we're doing it in chunks, we still can process when it's multiple indexes. So we would see 1 dash, so depth would be 1. Then we would go until we had seen all the values, and then val would be 4, 1. And then so on for this one, depth 2, and then 3, 4, 9. So we can take these chunks, and we can build our strings, or our values for our nodes. So let's just code that part first, because that's a little more straightforward. That'll be step 1. So we'll say int I, our index in the string that we're looking at, will be 0 initially. And then we'll say length is equal to traversal dot length. Then we're going to need a parent loop. This parent loop is going to be, for each iteration of this big loop, there's going to be an action performed. So each iteration of this loop is going to be a node being added to the tree. So we'll say while I is less than length. But within this big loop, we're going to need a few smaller loops. So we're going to need to do a few things. We're going to need to count all prepended dashes for depth. Then we're going to need to count all values for value. And this is for each chunk that we take out of the string. Then once we have all that, we're going to need to create the new node with value. And then we're going to have to place at correct depth. And that last step is going to be the most difficult to understand, so I will save it for last. But these first two aren't too bad. We can say while I is less than length, because we're going to be iterating past. We don't want to go out of bounds. And traversal is equal to dash. So while it's a dash, and we would create a depth here. Because the depth is given in dashes relative to the root, we can reinitialize depth to 0 each time, so we have a clean count. So int depth 0. And for every dash we see, we'll go one step deeper, so depth plus plus. And then we'll also increment I, so we can go to the next index. We've already seen this one. Once we break out of that, we need to get all the values before we hit another dash, so we know we have our full value for this node. So we'll say while I is less than length, same thing, we don't want to go to bounds, and traversal I is not equal to dash. You could also do this with like is digit or something like that. That'd probably technically be safer, but because we know we're only ever going to have a dash or a digit, I'm not going to worry about it. I'm just going to do it like this. So we'll say we're going to need another intermediate for our value. Because we're dealing with an integer for the node, but the values are actually charged within the string, we're going to have to do some conversion. And also, since we're going index to index and adding digits to their corresponding decimal place, we need to manipulate the integer in a way that it's almost like we're appending a digit instead of adding it to it, because otherwise it's not going to turn out right. So we'll say int val equals, and I'm realizing now that y'all probably can't see this too good. That might be better. Int val equals 0 initially. And then we'll say while I is less than length, so we don't go to bounds, and traversal is not a dash. We'll do val equals val times 10. So we're adding a digit to the current digit or value we have. So we need to shift everything over one decimal place. So we times by 10 and everything moves over a decimal place. And now we got a nice 0 in that last decimal place to add our next digit to. So we'll say val times 10. Then we need to convert the char to a decimal. So we'll say traversal I minus 0. And the idea here is if we just did traversal I, it would append the ASC2 value of the digit, not the digit's value itself. But if we subtract the char of 0, the offset is the true value. So we get what we want. And then same thing, we need to increment I. And once we break out of this loop, we have everything we need for the current block in the string like we talked about. So we can create the new node. So we'll say tree node, or we'll say next. New tree node. We'll use this value constructor right here. Tree node, and then val. So we have our new node. Now we got to do the hard part, and that's placing it. Well, if we really think about this, that left child priority kind of saves us here because we're only ever going to place a right child if we've already placed something to the left. And recursively, that works the same way. Like the deeper we go in the tree, and like let's say we go down the subtree here, we're going to see 1 and then 2, and then we see 3. So we're looking at 2's children, and then we see the same depth. So we need to go back. So we'll go back to 2. Well, since we went back to 2, we know that we're adding a right child because we'd only ever come back if there was a left child. So we come back and we do the 4. And then same thing, we go to the 5, we go back to 1. Well, if we came back from the left subtree, then we know we need to go right. So we can use that knowledge that anytime we do a backtrack, we're going to go to the right. And anytime we're going deeper, we're going to the left. That'll save us a little bit of confusion here. The other thing is the limitation of the tree in this problem is trees are great for going deeper within them, but there's no mechanism for going back because we don't have a pointer to the parent node. We only have pointers to children. So once we're deep, we can't get back if we don't track it somehow. So what we can do is we can keep a stack of these nodes, and as we create them and we go to the next depth, we push the parents onto the stack, and that way we have a corresponding structure for the depth we need. And when we need to go back, we can just pop them off. So let's look at this. So let's add a stack of tree nodes. We'll say nodes. And then let's kind of think about this. Well, on the root node, the stack will be empty. But the depth will be 0 because there won't be any dashes before the root. And the stack size will be 0. So they correspond. So we can say if depth is equal to nodes.size. If the stack size is equal to the depth, then we know that one of two things. Either the stack is empty and we need to add the root node in, or the stack's top element is the parent we need. Because when the root is the only element in the list and we go to the child of the root, well, the stack size will be 1 and the depth will be 1 for the child. So the stack size is kind of offset by 1. Whenever the stack size matches the depth you're targeting, the parent is the top element. So depth equals nodes.size. And then we have to account for that edge case where if it's not empty, the stack's not empty, then we need to add the left child. But if the stack is empty, then we're putting the root in. So we'll say while stack empty. So while the stack isn't empty, if the stack isn't empty, then that means the parent that we're targeting is the top element on the stack. So we'll say stack.top left equals next, the next node we created. And like I said, if we're ever going deeper from where we're already at, then we know we're going to be adding a left. So we're adding a left child to the top element of the stack, which is the parent we're targeting. So we add its left child. And then if the stack is empty and this doesn't work, then that means that we're at the root. This is kind of like an edge case. So we just do nodes dot push next. So we just add the root node. Now we need the other case. What happens when the depth is less than the nodes.size? That means that we're deeper in the tree and there are more parents within the stack than we need. So now what we can do is we can pop nodes off the stack until we get to the parent that we need, and we're back to the depth we need, and we had a way to backtrack to where we needed to go. So let's do else. while nodes.size is greater than depth. So while we're too far deep in the tree, we just do nodes.pop. We pop nodes off until we get to the depth we need. And once the depth and the stack size match, then we know that the parent we want to add the next child to is now at the top of the stack. Now, one more thing. Once this happens and we have the parent on top of the stack, the rule that we talked about earlier was anytime we backtrack, we know we're going to the right because we've already been to the left or we wouldn't be backtracking. So this time, instead of this stack.top left, we're going to do stack.top right. This time we add a right to the target parent. Okay. And then that kind of edge case we added for the root node works still because now that we've added the next to the tree, it is now the parent if we go any deeper. So we would need to push it anyway. So everything within this parent loop should be good. We go through the blocks, we get all the information we need from that block, we create a node to represent it, and then we place it at the correct depth by either going deeper or going back and going to the right. And then we keep adding the next node to the stack so that we can either go from it or we can pop it off if we don't need it and we can go back to our previous ones. Once we break out of this parent loop, now we only have to do one more thing. Since the stack represents the parents and we want to return the root so we get the whole subtree or the whole tree itself, we can do while stack.size is greater than 1. We're just going to, or sorry, it should be node. And this should be node. I'm bad about doing that. Node. Make sure I didn't do it anywhere. I did it here too. Nodes. Nodes. Okay. Sorry for any confusion there. Nodes.size is greater than 1. We just do nodes.pop. So we just pop off nodes until there's only one in the stack so that we know that the root is the topmost element. And then we just return the top element, which is root. Okay, let's give this a quick once over. Hopefully no typos in this one, fingers crossed. Let's try it out. There you go. All right. So a little complex, but when you break it down into chunks and you kind of think about pre-processing the input and then actually doing the placement, it's not that bad. Hope this helps.